So we need to prove this by mathematical induction. So here, case number 1, we have to show that this statement that we have is true for n equals to 1. So here, case 1 here, we need to show that the statement that we have is true for n equals to 1. So here, if this is true for n equals to 1, then the statement holds for n equal to 1 here. So what we're going to do here is, we get this, we equate it to what we have on the right hand side. So we have n squared equal to n plus 1 to n plus 1 divided by 6 here. So what is n here? We're going to substitute to the 1. So we're going to have 1 squared is equal to 1, open brackets, 1 plus 1, 2 multiplied by 1 here, plus 1, divided by 6 here. Then 1 squared is going to be 1, equal to 1 multiplied by this, we're going to have 2, then 2 multiplied by 1 plus 1, we're going to get a 3, divided by 6. So we have 1 is equal to 6 divided by 6. So this will just give us 1 is equal to 1. So therefore, this is true for n equal to 1. Okay. So now, case number 2 is just the inductive hypothesis. So here, we have the inductive hypothesis. So under the inductive hypothesis, we make an assumption that the statement that we have is true for n equals to k. So meaning that there, we just copy the expression the way it is, then where there's n, we substitute with k there. So we have 1 squared plus 2 squared plus 3 squared plus k squared is equal to k, open brackets, k plus 1, 2k plus 1 divided by 6 here. So this is the only thing that we get to do under the inductive hypothesis there. So now we go to case number 3, where we need to show that the statement that we have is also true for n equals to k plus 1 here. So here, case 3. So here, case 3, we need to show that the statement that we have is true for n equals to k plus 1. So how do we show that the statement is true for n equals to k plus 1? We're going to copy this expression the way it is there, up to the k term. Now, if we say k plus 1, it simply means that we're adding a new term now, which is the k plus 1 term there. So meaning that where there's n, we substitute with k plus 1, and so on and so forth there. So meaning that here we're going to have 1 squared plus 2 squared plus 3 squared plus k squared. So now, plus now, we're talking of the k plus 1 term. So we're going to say k plus 1 squared is equal to, where there's k on the right hand side of the expression, we substitute with k plus 1. So we're going to have k plus 1, k plus 1 plus 1, open brackets, 2, k plus 1 plus 1, then everything we divide by 6 here, like this. Now, when you look at these terms here, starting from the first term that you have here, all the way up to the k term, this gives you the left hand side of the inductive hypothesis here. So where are these terms here? We're just going to substitute with what we have on the right hand side. So here we have k plus 1, 2k plus 1 divided by 6 plus k plus 1 squared equal to, then this side we're going to have k plus 1, here that's going to be k plus 2, and there we're going to have 2k plus 3, so we have 2k plus 3 like this here, divided by 6 here. Now, this side here, we're going to make this a single fraction. So we know that this is the same as over 1. So meaning that if we make this a single fraction here, our common denominator this side is going to be 6 here. So 6 into 6, 1. Then we have k plus 1. And this side we have 2k plus 1. And there plus 6 open brackets k plus 1 squared equal to k plus 1 k plus 2 2k plus 3 here divided by 6 like this here. So our goal here is to show that the left hand side is equal to the right hand side. So we can choose either to simplify this or factorize this. So we'll choose, let's try to factorize what we have on the left hand side here. Then here, if you look at these two terms that we have on top here, k plus 1 is common there, so mean that there we're going to have our k plus 1 first, open brackets, we're left with k, 2k plus 1 plus 6k plus 1, we close like this, then everything here we divide by 6 here. So I'll just work out this side, then I'll write this later on the other side here. Alright, so inside the brackets here, you'll notice that we're going to have 2k squared. Okay, so here we have k plus 1, 2k squared plus k plus 6k plus 6, we close like this, divided by 6. Okay, let me just write this. So we have k plus 2 here, 2k plus 3, like this, divided by 6. So k plus 1, k plus 2, 2k plus 3, divided by 6 here. Okay, so now what we have inside here is going to be a quadratic expression. So here we have k plus 1, open brackets, 2k squared plus 7k plus 6 divided by 6 here equal to k plus 1, k plus 2 here, and then we have 2k plus 3 over 6 here. Now this here is a quadratic expression here. So this is a quadratic expression that we have there. So now here our product of that quadratic equation is 12, and the sum is 7. So two numbers we can multiply to get 12, 3 and 4. We add, we get 7 there. So mean that there we can just simplify this. We have k plus 1, open brackets, 2k squared plus 4k plus 3k plus 6 divided by 6 here. Let's still equate this to k plus 1, k plus 2, and 2k plus 3 here. Alright, so now let's try and simplify what we have here. So the common term that we have on the first two terms in the brackets there is 2k. So mean that here we're going to say we have k plus 1 like this, open brackets. So 2k is common between the first two terms here. So we have 2k, open brackets, we're left with k plus 2 plus what is common here is 3. So 3 open brackets, we're left with k here, then this side a plus 2 like this, we close them, we divide this by 6, then this side we equate it to k plus 1, k plus 2, 2k, also this is divided by 6 here, so plus 3, we divide by 6 like this here. Now inside there If we factorize what we have there, so we have k plus 1, then we're going to have k plus 2, then we have 2k plus 3 divided by 6 here is equal to k plus 1, k plus 2, and 2k plus 3 here divided by 6 here. So there we have it. The left hand side is equal to the right hand side, meaning that this expression that we have here is true for n equals to k plus 1. So therefore, true for n equals to k plus 1. So if this is true for n equals to k plus 1, then the statement that we have here holds under mathematical induction.